Hey everyone, we are going to be focusing in on entropy today and then tying in free energy a little bit, but then the rest of the week we will work on calculations related to Gibbs free energy. I'm going to go through it a little bit quickly just because you should have watched the crash course chemistry video first. So there's a couple of things I'll obviously bring back up in this video, but make sure you've watched that one as well. So what drives a reaction to be thermodynamically favorable? So we used to refer to this as being spontaneous, that would happen on its own, not necessarily fast, but that would be able to occur on its own. Now, really the phrase that we want to focus in on is, will it be thermodynamically favorable? So two big factors that play into this, and this is entropy, which we've talked, or enthalpy, sorry, delta H, which we talked about before, that has to do with your heat exchange. Exothermic reactions are generally favored, and you remember that that represents a negative delta H value. Entropy is their new component we're looking at, and it's actually, we use delta S for this. The disorder or dispersal of matter and energy of a system is what entropy is. So it's kind of how messy a system is, how disorganized a system is. We find that more disorder is favored. A common example of this is just your bedroom. If you put no effort into keeping your room clean over the course of a week, it becomes messier and messier. And next time your mom tells you to clean your room, you can blame it on entropy, but don't tell her I said that. All right. If we have a thermodynamically favorable process, we're going to be eventually reflecting this in terms of delta G, or Gibbs free energy. So these processes that are thermodynamically favorable are going to have a delta G that's negative, and we'll be coming back to that. So we'll be looking at the enthalpy component, but then also the entropy component. Now, where this kind of ties in terms of the laws of thermodynamics is the second law, where the universe is constantly increasing towards the dispersal of matter and energy. And that's really what gets at entropy. Be aware of the third law, where it focuses in on how entropy will only be zero if you have a perfect crystal at 0 Kelvin. So you might remember with like delta H calculations, we would have, enthalpy, and we would set, the enthalpy value for a pure element to 0, and you're going to see the same thing happen with delta G. But we actually can't do that for entropy, and that has to do with this third law. So just keep that in mind as we move forward. All right, what is entropy? If you can look at this next page with me, we just mentioned that this has to do with the amount of disorder. So it has to do or describes the number of arrangements, positions, and or energy levels that are available to a system existing in a given state. So it's related to probability. What are the many different arrangements of those particles? And the more arrangements you have, the greater the probability of those arrangements. And we know that nature spontaneously or favorably proceeds towards the states that have the highest probabilities of existing, the most amount of different arrangements. So this will kind of give you different graphics on here, which compared to the copy you might have, if you print it off, this is a little bit easier to see with the colors. But what I want to just focus in on first off is making sure you know entropy. Okay, that is the amount of disorder. Okay, which really just has to do with that number of arrangements, which is what this picture is getting at. Okay, how many different ways can you arrange 4 different particles in this case? So things that you're going to have to look for when you look at a reaction or a phase change or a process is how to tell, is entropy increasing or decreasing? Now they have this list down here, which is pretty extensive, and I want you to read through that, and I'll mention a couple things from it. But the two that you really have to focus in on is that number one, just examine the physical states. So for us, like if you think about solid, liquid, gas, most solids are very closely packed, arranged in nice, neat and orderly. So as it's melted or as it goes into a liquid phase, it's going to become a little bit further apart. They're going to be able to flow around each other. So the disorder increases, number of different arrangements increases. And then as you go to a gas, which are freely moving, you have the most energy or entropy. Keep mixing those up. Okay, so that's the first thing. The other thing I always get a question on is like with aqueous solutions. When solid or liquid phases go to an aqueous solution, you are increasing entropy. Okay, you're increasing, you're now mixing two things together, dissolving something, and you're increasing the entropy. This goes back to when we did our solutions unit and we talked about how even endothermic processes or dissolutions of compounds into water can still occur on their own, and it had to do with this idea of increasing entropy in that factor. So always first check those physical states. And then number two, if the physical states are all the same, just consider the number of particles that are involved. So with this, you would want to think of, oh, say you have 2 molecules of the reactant going to, say, 4 molecules of different products. This would be like, say, they're all in the gas phase. So if you're going from 2 to 4, well, 4 have a greater number of arrangements. There's going to create more disorder. So going towards this amount would increase the amount of entropy. Okay, so that's another thing. So usually those are the first two things you're going to check for. And that's kind of covered over here. You have the phase changes and so on. And you can kind of read through those. They get into a little bit more details that you can cover. You won't see too many questions this week on that. All right, so how do we predict entropy changes? We're going to kind of just apply what we were just talking about. So with this one, we have solid sugar that's being added water to form a solution. So we're going to just use glucose, so C6H12O6. This would be solid. I'm going to dissolve it into water. Make sure you don't actually put it in as a reactant because they're not reacting together. So now it's going to become aqueous. This would mean that we are increasing entropy because it's going from a solid to aqueous. So that will mean that when we increase entropy, we would have a positive delta S value to represent that increase in entropy. But say we have iodine vapor, and iodine is diatomic, okay, and it's a vapor, so it's a gas, and it's going into a crystal form or a solid form. Okay, in this case, we're going from a gas to a solid, so we are decreasing entropy. So this would be represented by a negative delta S. Another one that you could see would be, that's where you can see where all the phases are the same. It would be like the Hopper process. And say we just look at like the forward reaction, we're going from 4 to 2 in the forward reaction. So this would be a decrease in entropy. And I only looked at the number of particles because the phases were all the same. Now we can actually calculate entropy from different values. So with this, it's going to be very similar to how we did delta H. This is right on the AP reference tables, where we can get the delta S of the reaction based on products minus the reactants. Okay, we can see here just a summary. When delta S is positive, that means entropy is increasing. When you get a negative value, it means it's decreasing. One big thing with this is that entropy is always going to be in joules per mole times Kelvin, which is going to be different than enthalpy and Gibbs free energy, which will be in kilojoules. So just be careful when we get to some later lessons. So with this then, we can go ahead, we're going to plug in our delta S of our reaction. We're going to have our 2SO3, which is a product, minus 2SO2 plus O2. Okay, and then it's just a matter of just plugging them in and plugging them into your calculator correctly. So I'm going to have 2 times my 256.6 minus 2 times the SO2 value, 248.1 plus 1 times O2 here, which is 205.3. Okay, when you go ahead and actually plug those in, you're going to get negative 188.3. And again, make sure you're very careful here with units that would be joules per mole of the reaction per Kelvin. So this is showing that this reaction, based on our values, is showing us a decrease in entropy, which we would say would be unfavorable. So that's one calculation you could see in terms of our entropy. Even though we're going to focus in the next unit on free energy, I want to bring it up here. So the overall thermodynamic favorability of different processes and reactions is going to be summed up with this idea of free energy, or Gibbs free energy. So delta G ultimately decides whether a reaction is thermodynamically favorable or not. A negative sign on delta G, when we go to calculate this, indicates that the reaction is thermodynamically favored. So I first put the table up here just from the textbook. Just keep in mind, here delta H would be your enthalpy value, delta S would be your entropy, negative T delta S would just be this part of an equation that I'm going to show you in a second, which would then lead us to delta G, which is that free energy. And just keep in mind here, spontaneous is thermodynamically favorable, non-spontaneous would be thermodynamically unfavorable. And temperature plays a huge part in this. So one little thing would be, we talked about in the beginning that when delta H is exothermic or negative, and delta S or entropy is positive or increasing, it's going to be thermodynamically favorable. And it'll be thermodynamically favorable at any temperature conditions. Now, if those are flipped, if we have an endothermic reaction and we're decreasing energy, both of those are unfavorable. So it's going to always be unfavorable at any temperature. Now, when we look at, well, what about if it's only one versus the other? That's where we then have to consider temperature and how temperature will affect whether it's thermodynamically favorable or not. So how temperature is going to play in is going to have to do with this equation that we will be actually calculating with, where it takes free energy and allows us to calculate it from our enthalpy and entropy. So if we think about the different combinations, so this first one, and we're looking to get a negative value for delta G in order to be thermodynamically favorable. If both of them are positive, you want to think about this value. Okay, or really I should say this with the minus sign in there. We need to get that so that it's a really big value in order to cause this overall calculation to be negative. So by having a high temperature, that's going to cause this value to be large, which would then help to result in a negative temperature here. So we would say that if you have an endothermic reaction that's increasing entropy, it would only be thermodynamically favorable at high temperatures. Okay, so for that, the other thing is sometimes you'll see on an AP question, they'll talk about how this is entropy driven. And that just really has to do with the fact that entropy is positive, so it's favorable. That's going to help drive that reaction to be thermodynamically favorable as long as it's at a high enough temperature. Now, if they're both negative, so we have an exothermic reaction, but we have a decrease in entropy, so kind of, again, one or the other, this is only going to be thermodynamically favorable at low temperatures. And again, it has to do with this expression here. You have a negative delta S, so we need to keep our temperature low in order to, because we know negative times a negative would be a positive, we need to keep that value low enough in order to keep our delta G negative. And that's why, again, you're going to see up here, both of them are negative. It will only be thermodynamically favorable at a low temperature. The other thing is this type of reaction we would say is enthalpy driven. So enthalpy is favored. Okay, and so this will only occur if it's at a low temperature in order to occur. So just a couple things to kind of keep in mind as we go forward. We'll be working on a bunch of calculations in the next video.